This episode, I'm speaking to science author and former radio astronomer Marcus Chown about his latest book, A Crack in Everything. It's a history of the people and discoveries that have led to our current understanding of black holes. I spoke to Marcus about what black holes are, how they were first conceived, and how their very existence raises fundamental questions about the structure of the universe.
Yeah, my name is Marcus Chown. I'm a writer and broadcaster. I was formerly a radio astronomer at Caltech, the California Institute of Technology in Pasadena.
Thanks very much for coming on the podcast, Marcus. It's great to have you.
Well, great to be on it. Thanks.
The reason we're talking today is because of your latest book, A Crack in Everything, will be coming out around about the time this podcast's out, I think. And it reads like a history of our understanding of black holes. I wanted to kick off with that title. What is the crack in everything?
Well, I mean, basically, the major theories of physics, which are general relativity, which is a theory of big things like the stars and galaxies in the universe, and a theory of small things, quantum theory, a theory of atoms and those kind of things, and thermodynamics, a theory of heat. They all collide in black holes, and they all predict different things for the same situation. And for physicists, that's gold dust, because it means that one or more of those theories is incorrect. So really, the crack is the crack in physics itself.
Right, amazing. When you were talking about there's different disciplines, and the book sort of plays out like that. I think it plays out like it's different stories of different individuals at different points in time that have led to our current understanding of gravity and black holes. And I wanted to get your thoughts on this as a scientist. Do you feel that that's the way scientific progress is made? Because you could sort of think of science as like a sort of accumulated knowledge, but reading the book, it feels like there are like specific points in time and specific individuals who make certain leaps and propel everything forward. Do you think science? Think that's a more accurate way of depicting science?
I mean, I'm fascinated by the way that science is done, because it's actually kind of like a drunkard's walk, you know, and there's often people going down dead ends, getting the right answer for the wrong reason. I mean, for instance, George Gamow came up with the idea of the Big Bang, but he thought there was an oscillating universe, so he got the right answer for the wrong reason. So that's the way it normally is done. But this particular topic, there were a number of individuals who were really important. And interestingly, my editor said to me, towards the end of the book, you don't seem to be talking about individuals. You seem to be talking about big teams of people. Can't we talk about individuals? And really, because this topic spans the last 100 years, there has been a fundamental shift in physics from individuals being able to make huge contributions to only giant teams. So actually, the book documents that. So I've tried to. So it's very, very easy in the beginning, because there are people like Karl Schwarzschild, Einstein, Subramanian, Chandrasekhar, these kind of individuals. Roy Kerr, in fact, who the New Zealander who found the description of the space-time around a spinning black hole. These are individuals, but then you move to these great teams of people like, the Event Horizon Telescope, large team of people get the first ever image of a black hole. So yeah. I mean, again, as a writer, you're trying to impose a kind of logic on it, and of course, this is not the way it was actually experienced by the people. For a lot of certainly the first part of the 20th century. I mean, really, people didn't think that black holes were serious. They didn't think that and if they were, they would be black, and they would be small, and therefore they would be invisible, and so there would be no point in searching for them. So again, a lot of the people in physics, in the history of physics, often people don't even know the questions, but we, looking back with hindsight, can impose this structure, and that's what I've tried to do.
Amazing. Yeah, I mean, one of the individuals you mentioned was Karl Schwarzschild. The book sort of opens with him lying in his hospital bed in the First World War, and it's the idea that he comes up with the idea of a black hole from there. So it's not from having observed anything with a telescope or having run simulations through a computer. He essentially comes up with it with mathematics and a pen and a piece of paper. How is it possible that he did that?
Well, it's very interesting because you asked me about my book, A Crack in Everything, but my previous book was called The Magicians, and then it was called Breakthrough in paperback, and it was precisely about that. It's about how, with modern science, discoveries are made on a piece of paper by someone scrawling symbols on a piece of paper. So it starts with Neptune in the 19th century, when Urbain Le Verrier in Paris, he predicts the existence of this planet and tells people exactly where to find it. And now, to me, that is the kind of central magic of science, that you could scroll these symbols down on a piece of paper and they can predict things in the real world that no one has ever suspected, and we go and find them. Things like the Higgs particle, things like black holes. And I think this is an incredible miracle, because it means that there are two universes. There's the universe that we live in, and then there's a mathematical universe that you can write down on a blackboard, on a whiteboard, on a piece of paper, and it is an exact analogue of the real universe. And nobody knows why that's true. I think Paul Dirac, the famous British quantum physicist who was born in Bristol, I think where Sky at Night magazine is based, he said God must be a mathematician, but we don't actually know why the universe has this complete parallel, this complete analogue that you can write down on a piece of paper. So my last book was all about examples of that. So you've actually got off the subject of my current book.
Let's get back to black holes then, because one of the points that you make in the introduction is they are neither black nor holes. Do you think is there a misconception amongst the general public, and is therefore the black holes not a particularly accurate name?
Well, it's a fantastic name, because again, you can see in the 20th century very, very little interest or investigation of black holes theoretically, or even very little thought that they could actually be detected. And that's because there was no name. And then in 1967, John Wheeler, who was the supervisor of Richard Feynman, comes up with his name. In fact, he always said it wasn't he who came up with the name. There was a student. He kept talking about these, these warpages of space-time, and then somebody in his audience, a student, said, well, why don't you just call them black holes? So he then introduced the term, and then suddenly you get this explosion of interest in these things, because there's a term that paints a vivid picture in people's minds. And we now talk about, losing something down a black hole if we've lost our, a letter or whatever. So it's entered the language, and there's pretty much nobody on the planet who doesn't know the phrase black hole. But as you point out, one of the central characteristics of certainly the black holes that we've discovered is that they are blazingly bright. In fact, they are some of the most luminous objects in the entire universe. And far from us seeing material sucked in, one of their central characteristics is that material is coming out. So we see the supermassive black holes in the center of galaxies, big galaxies, with these incredible jets of material that come out, oppositely directed from the poles of these spinning black holes and extend across millions of light years. So obviously they are sucking in material, but that isn't very obvious. So yeah. I mean, unfortunately, it's a term that has stuck. And it does, I suppose, give you the idea that material falls in and never comes out. But yeah, they're not black at all. And that really did surprise people. And it shouldn't have surprised people, because everything in the universe is spinning. So, stuff is not going to fall directly into a black hole because it's got angular momentum, because it's spinning. It will swirl around the hole like water running down a plug hole. And of course, we now know that friction within that gas will heat it to millions of degrees. And of course, what we see is not directly the black hole, but the blisteringly hot accretion disk around black holes, which make them so phenomenally luminous.
Yes, and that's, people will probably recognize that from an image of a face-on spiral galaxy. Isn't that bright center, that is that always, or is it just largely speaking mostly as a result of the supermassive black hole at the center of that galaxy?
Well, so one of the things we discovered, first of all, we thought black holes were too ridiculous to actually they're not even a preserve of science fiction. And then we begin to think that maybe they're not. Then we discover them. And then we discover that they power some of the most powerful galaxies in the universe. About 1% of galaxies, as you rightly say, are active galaxies. That means that most of their light does not come from stars. It comes from the accretion disk of around a supermassive black hole. So a black hole which is maybe millions to tens of billions of times the mass of the sun. And that makes these objects, and the most famous example would be quasars, makes these objects phenomenally bright. So their nuclei are so bright that it took a long, long time, probably 20 years, before our telescopes, our detectors were good enough to detect the stars around, because this is basically trying to detect only a few fireflies when there's a whopping great searchlight in your eyes. So yeah, these objects, these accretion disks, pump out about 100 times, sometimes 100 times, maybe even 1,000 times the energy of the stars, and completely wipe them out. So yeah, they are phenomenal. But of course, what we've also discovered, which is another, we thought they were, even when we discovered them in galaxies, we thought they're still anomalous, they're still not important, they must be peripheral to the universe. And then of course we discovered that in fact they're in every single galaxy. And the reason we only see them in 1% is because in 99% of galaxies they're slumbering.
Oh, what does that mean?
They're not active, so they've run out of food. So that this was a major discovery, because black holes. My book is called "How Black Holes Came in from the Cold and Took Up Cosmic Central Stage." So they're considered to be these incredible anomalies which are of no significance to the universe at all. And then we find that they're in 1% of galaxies, powering things like quasars. And we can still say, well, they're not very significant, that's only 1%. But then in the 1990s, the Hubble Space Telescope was able to look, because it was above the atmosphere, above the distorting atmosphere, it had very sharp vision. It could look into the centres of many nearby galaxies. And in every single one, the stars were whirling around far too fast. And therefore, they were in the grip of some kind of concentrated mass. So during the 1990s, the Hubble Space Telescope discovered that there was actually a supermassive black hole in every galaxy. And of course, that's one of the great mysteries. Why is there a supermassive black hole in the centre of every galaxy, including our own? We've got no idea.
Yes, and as I understand it, isn't there a sort of chicken and egg question as to does a black hole form first and then the galaxy around it, or the black hole form within the galaxy already?
Exactly right. We've got no. We don't know. We really don't know. We're hoping that the James Webb Space Telescope will shed some light on this. It can look back to very, very early times. It's seen quite large supermassive black holes very early on in the universe. So we don't know. You're right. Whether maybe a gas cloud collapses to form a supermassive black hole, and then the galaxy kind of accretes around it. The gas accretes around it, which later becomes stars, or whether the stars form first. And then maybe in a cluster at the centre, they begin to collide, form black holes, which merge, and you get supermassive black holes. But this is, again, a huge problem for astrophysics, because we see evidence of these supermassive black holes extremely early on, within the first few 100 million years, maybe 200 or 300 million years of the Big Bang. And it's very hard to see how they could grow that quickly. So there are two problems. There's two problems. You need to get a big black hole. You need a reasonable seed to start with, and then it needs to be able to accrete material. And as far as we know, the first generation of stars to form after the Big Bang, the first stars to have formed in the very first galaxies, we think they were a bit more massive than the ones. There's a reason for believing that they were more massive. They were called population 3 stars, and they would have left relatively big black holes, maybe 20 or 30 times the mass of the sun. But that doesn't seem to be big enough a seed to end up within maybe 500 or 700 million years of the Big Bang of something that weighs almost 1 billion solar masses. The big problem is that as they accrete material, the accretion disks become extremely hot, and the radiation pouring outwards pushes away any incoming materials. So there's what we call an Eddington limit to how fast a black hole can grow. So to get some of the biggest ones that we're seeing in the early universe, you need very large seeds, and you need them growing at absolutely the maximum rate possible. But it's not clear whether that's going to be enough. So again, the whole point of my book is that these objects have become central to galaxies and our being here and all that kind of stuff. But the big questions about where they came from, what they're doing in the center of all galaxies, how they got so big so quickly, they're not known.
It's sort
the
of
answers are not known.
It sort of reminds me of at the time of recording that there's a lot of discussion about Webb's discoveries and looking into the early universe, and it's seeing sort of things that, according to our understanding of the universe, shouldn't exist. Galaxies and things that technically shouldn't exist. So does that sort of give you hope that powerful observatories like Webb will be able to solve mysteries like that?
Definitely, and I mean, again, it's gold dust to physics. You started off by asking me about why the black holes are a crack in everything, and it's because they show us where physics breaks down, and that's a great help to finding a better, deeper theory of physics, than we actually currently have. So again, they are telling us in the universe that we don't understand galaxy formation, because obviously black holes are a major ingredient. We don't understand them, so we don't really. I mean, I don't think we're talking about the total breakdown of astrophysics, but it's very exciting when we know that there's something big that's missing. We don't understand. I mean, one of the most bizarre things about the supermassive black holes is they are incredibly tiny. I mean, they are. So a supermassive black hole is like pretty much like a bacterium compared to London. So you would expect that it would have no effect on its galaxy. And in terms of mass, generally they are about a 200th the mass of even the central bulge of stars. So no one expected that they would have any effect whatsoever on their large-scale galaxy. Their gravitational influence shouldn't extend more than 10 or 20 light years, when the central areas of galaxies are maybe 20,000 light years across. And yet it was discovered again since the year 2000 that they have left an indelible print on the stars in their galaxy. So, for instance, in pretty much every galaxy we see, current galaxy, we see that the stars are about 200 times the mass of the supermassive black hole. So there's a link. They've obviously grown together and influenced each other. But there's something, does a bacterium control the street plan of London? And yet these tiny objects do clearly, they can't today, it's impossible, but they must have done very early in the galaxy's history. And really, I think the key is not size does not matter, it's actually the energy. So if you walk past a house and a slate falls on your head, it hurts. And that's because what we call gravitational potential energy, that's the energy that the slate had by virtue of its position in the gravitational field, has been converted into kinetic energy, and hit you on the head. So when you form a supermassive black hole of billions of times the mass of the sun, it's like God knows how many quadrillion slates all coming together. And the energy required to do that is about 1,000 times more than the energy necessary to actually explode the galaxy. So in other words, blow apart all of the stars to infinity. So there's more than enough energy there for the formation process of a supermassive black hole to leave its imprint on the gas, which later forms the stars, and leave some kind of imprint. So this is why, I mean, it is bizarre that until this was it was realised that this imprint had been left, we were missing a major ingredient in our understanding of how galaxies form. Literally, galaxies make no sense whatsoever if you don't know about supermassive black holes. They obviously played some key role in the formation of the stars early on in galactic history.
I mean, just listening to you talk and explain all this, it's incredible that they were ever sort of ignored and dismissed, isn't it? I mean, and now it's exploded. It reminds me of It reminds me a bit of sort of the explosion of exoplanet study over the past sort of 20, 30 years. Nothing, then one's discovered, and then the whole field just explodes and everyone's talking about it and goes from individuals to massive teams. Feels like a similar story.
Well, it does. It does, And as I say, I document in my book how they went from, being basically so ridiculous as to not be even considered. Remember, they are a prediction of Einstein's theory of gravity. He didn't believe in them. To gradually, it's as if physicists and astrophysicists have been dragged kicking and screaming to this realization that they play some enormous role in our universe. And in fact, we're only having this conversation because of the supermassive black hole in the center of our galaxy. Sagittarius A star is a tiddler. We've got no idea why it's so small. We should have a black hole of about maybe 500 million solar masses in the center of our galaxy. If we were like Andromeda, if we were like other galaxies, but we've got a real tiddler, which is about 1,000 times smaller than you'd expect for a galaxy of our size. But then if you think about what it would be like in the galaxies with the really big supermassive black holes, they have these jets, they have these incredible accretion disks which glow at millions of degrees. So there's these huge outflows of material coming from them, heat and matter, driving away. It drives away the raw material that would make stars. So in these really big galaxies with the big supermassive black holes, we see only one generation of stars. So very early on, stars formed, and then all the gas got blown away, and those stars would have been stars made from the pristine material from the Big Bang. So they would have only had hydrogen and helium, wouldn't have had the heavy atoms like calcium and neon and all these other things. And all of those things like calcium and carbon are necessary for life. So the big galaxies with the big supermassive black holes would be biological wastelands. There would be no planets made from heavy elements like the Earth. There would be no biology. So here we find ourselves in this galaxy with a very tiny supermassive black hole where none of the gas has been blown away. And we've had multiple generations of stars. So our sun is believed to be a third generation star. So, the first generation cooked some heavy elements. They were splurged into space when those stars exploded. They became the raw material of the next generation. So we find we live in a galaxy which is contaminated with the elements of life. But So I mean that's probably why we're having this conversation. There's no way we could have arisen in a galaxy with a very large supermassive black hole.
Does that also then raise problems if you try and look at the probability for life existing in our galaxy and extrapolate that out into the wider universe, because you can't use our galaxy as a typical galaxy, given what you just said?
Probably, yeah. And again, we increasingly find other things. We've got a big moon, as you know, which is very big, probably the biggest moon compared to its planet, apart from Pluto. But then it's a dwarf planet. It has a moon called Charon. But again, and we think that played a big part in us being here because it stabilized the Earth's spin. So, we like a spinning top, the Earth does not waver. So the climate has remained pretty stable over billions of years, necessary for the evolution of life and whatever. So increasingly, we do see these things, like we're in this unusual galaxy with a very small supermassive black hole for its size. We have a very large moon. All of these things certainly make it seem as if life, as we know it, might not be very common, but maybe there's life the way we don't know it. Who knows?
I also wanted to talk, just as I sort of get to the end of the podcast, I wanted to talk about sort of your own personal relationship with black holes, because you talk in the book about going to a lecture as a young kid and the impression that had on you. Are black holes the reason you got into science, do you think?
Well, I mean, when I was at school, I never realised that astronomy was actually anything to do with. They never mentioned astronomy at school, but then I was very lucky. Obviously, you can probably tell from you're looking at me. I've got slightly grey hair, but I was unbelievably lucky to be a 9-year-old. When the first human being stepped on another world. And I can't, I mean, there's a shiver going down my spine even telling you about that. You know, my dad got me up to see that when I was, you know, to see these fuzzy images, and it just blew my mind, you know. And my dad, who left school when he was 15, I mean, he'd grown up during the war, you know, they had no schooling or whatever, bought me a book on astronomy when I was about 8 or 9. It was called Dr. H.C. King's Book of Astronomy, which was he was the director of the London Planetarium, and I just got really into it. I had a small telescope which I poked out of the window of our council flat in North London. I used to you know, look. I could see Jupiter's moons above the orange glow of the North Circular Road. You know, so that's what kind of got me. And then I was a member of the Junior Astronomical Society, and you just mentioned that I went to. My dad took me to a meeting in Victoria, in London, and a man on crutches hobbled towards the stage. I didn't realise that it was because he'd had polio. His name was Paul Murdin, and he talked about Cygnus X1, which was the first black hole to be discovered, and it just blew my mind, you know. So interestingly, I got to interview him, you know, and I don't think people remember who he is. You know, there have been 3 Nobel Prizes for black holes now. No one ever mentions who discovered them, and in particular, the co-discoverer, Louise Webster. So really, if you really want to say what my book is about, it's really about people. You know, it's about, and I really want Louise Webster to get the credit that she deserves, because she was the co-discoverer of black holes. She's been basically forgotten, written out of the history of science. Unfortunately, she did have, well, she was fortunate to have one of the first successful liver transplants in Australia, but then she contracted cancer and she died at age 49. Nobody remembers Louise Webster. So now, if you think about it, the 2 endpoints of the lives of massive stars, you know, what we call relativistic stars. So the 2 types of stars that can only be understood using Einstein's theory of gravity, they are pulsars or neutron stars, and black holes were both discovered by women.
Absolutely, yeah. And
one of whom, of course, is from Northern Ireland.
That's right.
I'm guessing by your accent, you're from Northern Ireland.
Yeah, that's right. From Lurgan, I believe. She's from.
Yeah, you know, and 3 Nobel Prizes have gone for pulsars, and not one has gone to Jocelyn Bell. And you know, Louise Webster's in a worse position, where she's been entirely forgotten. I've never met an Australian who knew her name.
I think you're right, though, that's sort of like one of the really interesting things about the book is that it is a story about people, and you probably open the book as a reader thinking it's going to be a lesson in science, but it's a lesson in sort of history and moments in time, you know, when science was propelled forward. If you sort of fast forward from you as a kid, seeing Paul Murdin speak, and then fast forward to sort of like 2019 and that first image of the black hole and that came through, what did that mean to you when you saw that, you know, for the first time?
I just think it was astonishing. It, to my mind, that's one of the most the key images in the history of science. You know, I mean, we all know that the rising of the Earth above you know, the lunar surface, you know, seen by Apollo 8, one of the great images in the history of science, maybe the first image of DNA spiral. But I think to see that image of a black hole was absolutely incredible, because inside a black hole, we know that, well, we believe that space and time actually come apart. We don't actually have a theory that describes what actually happens when that happens, but we think that they just come apart. So I often think, you know, that we do have a tendency to beat ourselves up and think, you know, we're human beings. We've overpopulated the planet. You know, we've triggered global warming, pollution, all these kind of things. But I think sometimes we need to just pat ourselves on the back and think, you know, we are, you know, we came down from the trees 3 million years ago. We have a brain the size of, you know, 3-pound brain that's made of jelly and water, but we have seen to the edge of space and time. And I think that's an incredible thing.
Fantastic. Yes, that's quite a nice note to end on, Marcus. Thanks very much for talking on the podcast and talking to me and about your book, A Crack and Everything, which, as I say, should be out around the time this podcast goes out. But yeah, hopefully you'll come on when your next book's out and
great. Yeah,
chat a bit more.
Thank you very much. I really enjoyed it. Thank you.